Picture this. Two massive drilling machines, each weighing 1,500 tons, grinding through solid rock beneath the English Channel. They're heading toward each other from opposite shores. Britain and France. If they miss by even a few inches after boring 31 miles underground, the entire $15 billion project collapses. On December 1st, 1990, French worker Philippe Cosette broke through the final wall of chalk. On the other side, British worker Graham Fagg. They shook hands 131 feet beneath the seabed, connecting two nations that had been separated for 8,000 years. American engineers said it couldn't be done. They were wrong. This is the story of the impossible tunnel that changed Europe forever. For nearly 2 centuries, engineers dreamed of connecting Britain to mainland Europe. Napoleon proposed the idea in 1802. The English Channel, just 21 miles at its narrowest, had been a natural barrier since the Ice Age. Ferries took hours, were weather dependent, and couldn't handle 20 million passengers yearly. By the 1980s, the economic case was undeniable. Trade between Britain and Europe totaled over $100 billion annually, yet transportation remained slow. Prime Minister Thatcher and President Mitterrand faced a challenge. Build a 31-mile tunnel without government funding. The numbers were staggering. The tunnel would need to withstand tremendous water pressure of 10 atmospheres, accommodate trains traveling at 100 miles per hour, and require 3 separate tunnels, 2 for trains and 1 for service access. And here's the kicker. It all had to be done by private investment alone. No taxpayer money allowed. The planning phase began in 1984 when Britain and France signed the Canterbury Treaty. But how do you plan the engineering project of the century? Geologists spent years carefully surveying the seabed. They discovered a crucial advantage. A layer of chalk marl, a dense, impermeable rock formation, ran continuously between Folkestone, England, and Coquelles, France. This blue-gray chalk sits about 130 feet below the seabed, creating a natural waterproof barrier, perfect for tunneling. The route was finalized, 31.4 miles total, with the deepest point reaching 246 feet below the seabed. Satellite surveys and sonar mapping created detailed 3D models of every geological feature. 10 different construction consortiums submitted competitive proposals. The winning bid came from Transmanche Link, a partnership of 5 British and 5 French construction companies. Their ambitious plan: build from both sides simultaneously using tunnel boring machines, meet in the middle with laser-guided precision, and complete the entire project in just 7 years. Environmental assessments examined impact on marine life and coastal ecosystems. Safety regulations demanded escape passages every 1,200 feet and evacuation procedures for up to 1,000 passengers at once, but the real challenge was still ahead. The Channel Tunnel required technology never used at this scale. At the heart, 11 custom-built tunnel boring machines, each costing $15 million and stretching 700 feet long. Longer than 2 football fields, these weren't ordinary drills. The rotating cutting head measured 28 feet in diameter, equipped with 108 tungsten carbide teeth, grinding through chalk at 250 feet per day. American engineers were skeptical. Their largest machines were half this size, and behind the cutting head, hydraulic rams pushed the massive machine forward while installing precast concrete segments. Each concrete ring consisted of 8 curved segments weighing 8 tons each piece. The machines manufactured and installed these automatically, automation that seemed impossible in 1987. Material requirements were astronomical. 4.5 million cubic yards of chalk removed, creating a new 90-acre park in Kent. The project consumed 3.7 million cubic yards of concrete, enough for 120,000 homes. Steel totaled 300,000 tons. Engineers developed special concrete with ultra-low permeability, withstanding 10 atmospheres of pressure. Rubber gaskets between segments created watertight seals. How could this work beneath one of the world's busiest shipping lanes? On June 28, 1988, the first machine, nicknamed Europa, began grinding into the white cliffs of Dover. Across the channel, French machines started simultaneously. The race was on. Working 24 hours a day, 15,000 workers descended into the tunnels. Conditions were brutal. Temperatures reached 95 degrees Fahrenheit, humidity hit 100%, and the air was thick with chalk dust despite massive ventilation systems. British and French teams used different approaches. British machines excavated the full diameter immediately, installing concrete lining as they progressed. French machines dug smaller pilot tunnels first, then enlarged them. Each method had advantages which would prove faster. Unexpected challenges emerged. At the 9-mile mark, British tunnelers hit a water-bearing fissure. Water poured in at 1,000 gallons per minute. Work stopped for 3 weeks while engineers pumped in liquid nitrogen to freeze the ground solid. Precision was everything. Laser guidance systems, accurate to within 2 inches over 30 miles, kept the tunnels on course. Any deviation would be catastrophic. The 2 sides had to meet perfectly. In October 1990, British and French crews could hear each other's machines through the final 300 feet of chalk. What if the calculations were wrong? On December 1st, 1990, Philippe Cosette's drill broke through. The tunnels aligned within 1 inch horizontally and 2 inches vertically, an engineering miracle. When Cosette and Graham Fagg shook hands through the hole, they made history. But completing the bore was just the beginning. Now came transforming raw tunnels into a functional railway system. 3 more years of intensive work. Trains traveling at 100 miles per hour would create massive air pressure waves. Engineers designed crossover passages every 1,200 feet to equalize pressure between tunnels. Without these, passengers would experience painful ear popping. The tunnel required 100 megawatts of electricity, enough for a city of 100,000 people. This powered 50,000 lights, ventilation, pumps, and the 25,000-volt overhead system for trains. Cooling was critical. Engineers installed refrigeration equivalent to 9,000 home air conditioners. Cold water circulated through pipes along tunnel walls, maintaining 65 degrees Fahrenheit. Safety systems were revolutionary. Fiber optic networks, fire detection sensors, and cross passages every 1,200 feet allowed emergency evacuation. Computer systems monitored 20,000 sensors tracking air quality to structural stress. But would it all work when tested? Before passengers could board, the tunnel underwent rigorous testing. Engineers scanned every inch of concrete with ultrasonic equipment. Ground-penetrating radar mapped surrounding geology. Pressure tests simulated trains at full speed. Test trains began in March 1994, starting at 20 miles per hour and gradually increasing. At 100 miles per hour, air pressure created winds strong enough to knock a person over. Fire safety tests were intense. Engineers set deliberate fires, measuring smoke spread. Evacuation drills with 500 volunteers simulated escaping burning trains in darkness. The final test came November 1st, 1994, a complete dress rehearsal with real passengers and freight. Minor issues emerged. Engineers made 200 adjustments. American observers remained skeptical, but British and French regulators certified it as the world's safest high-speed rail system. On May 6, 1994, Queen Elizabeth II and President Mitterrand officially opened the Channel Tunnel. The impossible had become reality. The impact was immediate. Travel time from London to Paris dropped from 6 hours to 2 hours 15 minutes. Within 5 years, 3.5 million trucks annually used the shuttle service. The tunnel created a new European economic zone. Property values in southeast England and northern France increased 40%. Trade between Britain and the EU grew by 18%, $120 billion in additional commerce. Environmental benefits were substantial. Shifting 1 million trucks yearly from ferries to rail reduced CO2 emissions by 2.2 million tons. Noise pollution in port cities decreased dramatically. Culturally, the tunnel bridged an 8,000-year divide. French families could weekend in London. British students could study in Paris without flights. Over 450 million passengers have crossed since. Financially, the project cost $15 billion, 80% over budget. Private investors lost billions initially. Profitability didn't arrive until 2007, yet governments gained through increased tax revenue without risking taxpayer money. For skeptical American engineers, the Channel Tunnel proved European engineering could accomplish the impossible. It inspired projects worldwide, the Goddard Base Tunnel, the Second Tunnel, and proposals linking continents. Today, the Channel Tunnel stands as a monument to human ambition, connecting 2 nations beneath one of the world's busiest waterways. 2 countries, one impossible dream, 15,000 workers, and 7 years of drilling through solid rock beneath the sea. The Channel Tunnel redefined what engineering could achieve.